All right, so we're going to let u equal x squared here, since that follows the trig function sine. We're introducing a new variable, so we set up a new problem. The reason we're letting u equal x squared is because, again, that follows sine, so we write sine of u over here. We still need to replace, because now we've taken care of this part, the sine of x and dx. So that's where taking the derivative of this equation comes in over here. Take your derivative, get du equals 2x dx. We're trying to replace a 6x dx. We've got a 2x dx here, so if we just multiply both sides by 3, that'll give us the 6x dx we're looking for. So 6x dx equals 3 du. I put 3 du over here in my new problem. Now remember what we talked about last time. If you're going to use u substitution on these problems that are definite integral problems, we're now converting over to a new variable. The original interval was in terms of x. So now we have to adjust that interval so it's in terms of u. We're going to take our 0 here, we're going to plug in for x down here, square that, obviously get 0 back. That's going to be where the new interval begins over here. Then we're going to take the square root of pi over 2, we're going to plug that in for x, we're going to square that. So we square the square root of pi, we get pi. We square the 2, we get 4. Pi over 4 is going to be where this new definite integrals interval ends. And now we got a new problem. So with our new problem, take your antiderivative of 3 sine of u. The 3 in front of the trig function just coming along for the ride. You're taking the antiderivative of the sine of u. Do you get cosine of u or do you get negative cosine of u? Negative cosine of u. So we could just say negative 3 cosine of u, right? We still have to acknowledge the interval. At this point, applying first fundamental theorem, we're taking the pi over 4, we're plugging in for u. We've got negative 3 cosine of pi over 4. And from this, we are subtracting negative 3 cosine of, replace u with 0. Do some calculations. We arrive at our answer. 7, 9. So it makes sense on this one. We're going to let u equal the exponent on the e, which is 1/2 x to the 4th. So we introduce the new variable, we set up the new problem. We're letting u equal the exponent on e, so we're able to replace this part as e to the u. And now we're looking to get rid of or replace the 2x cubed dx. So take your derivative of the u equation, get du equals, bring down 4, multiply to 1/2, get 2x cubed dx. And that was way too easy, right? We're trying to replace 2x cubed dx. There it is. Apparently 2x cubed dx can equal du, so we just insert that over here. Got the new problem in terms of the new variable u. Old problem was in terms of the variable x, so set up a new interval. If I plug in 0 down here for x, u is going to be 0. And if I plug in 1 down here for x, 1 to the 4th is 1 times 1/2. This new interval ends at 1/2. So we got the new problem. We take the antiderivative of e to the u, which is e to the u. Acknowledge the interval we're working on, 0 to 1/2, and now plug in. We plug in to this power, we've got e to the 1/2 minus e to the 0. We actually write the answer a couple ways here. E to the 1/2 is the square root of e. E to the 0 is 1. Or if you calculate that out, decimal to 3 places is 0.649.